Dear students, hope you guys are doing well. I would like to start today's discussion by recalling what we were doing towards the end of the last lecture. Remember, we were talking about volume of the solid under the graph of the function with two inputs and over the rectangular region. Let me remind you the result again. I would like to give you one very quick example before moving on to the next topic. The statement was very simple. It was about volume of a solid. Let z equal to f of xy be a non-negative function. Remember, we want function to be non-negative on a rectangular region R consisting of ordered pair of the form x comma y, where x value sits between numbers a and b and y value sits between numbers c and d. Then the volume of the solid under f of xy and over R is given by simply a multiple integral of the given function over respective area. Remember, this dx dy I read it as respective area. This doesn't mean variable x needs to go first and then y. You guys will have to decide by looking at the bounds of x and y and integration technique that is being used to integrate function f of xy. Alright, let me give you one very quick example. Let's say find the volume of a solid under the graph of z equal to f of xy equal to, let's say we have 6x square y e to the y square plus 1 and over the region R that is bounded by, that consists of ordered pair of the form x comma y, where x value, let's say it's between -2 and 1 and y values are between 0 and 1. Okay, let's try to first set up the problem. As I said, setup of this problem is the most important step, and if that step is correct, then highly likely remaining steps are correct too. What I mentioned last time was this, that if you are integrating your function over a rectangular region, then Fubini theorem guarantees that it does not matter whether you integrate first with respect to x or with respect to y, you are gonna get the same result. Unfortunately, if you use one of the variable randomly, sometime it may lead to lengthy computation. So you really would like to make a selection of variable based on the corresponding integration technique that you are going to use. Alright, let's try to do the setup first. So here is the volume formula. V is multiple integral of my function with respective area over the of the rectangular region R. Remember how I asked you to set up the problem. First I write down my function 6x square y times e to the y square plus 1. Now think about it for a second, that what technique are you going to use to integrate this function with respect to x? Which technique do you need if you were supposed to integrate this function with respect to y first? Alright, let's think about variable x first. So first of all, if you are integrating it with respect to x, I would treat y as a constant. So altogether this is just one term. Seems like I read this function as constant times x square. We know how to integrate constant times x square. Direct matching or power rule for integration is needed. So integration with respect to x requires us to use really the power rule only. Alright, now think about it. What integration technique is required to integrate this function with respect to variable y? Well, I read it in terms of y first. Constant times y e to the y square plus 1. Now recall that y e to the y square plus 1, this particular function, in order to integrate it, you will need u substitution. So obviously the simpler method is recommended to go first. So variable x only requires power rule. So I would integrate this function first with respect to variable x, and then I will integrate the remaining part with respect to y with the corresponding y bounds. Alright, let's do this carefully now. Integrate this with respect to x. We are going to treat y as a constant. Antiderivative of that x squared term is going to be x to the 3 over 3, and then all the constants that are multiplied with y will stay there. I would like to evaluate this when x is negative 2, when x is 1, and I would like to calculate the difference. And then the result will be integrated with respect to variable y. Okay, let's simplify this first before we use fundamental theorem of calculus. I get integral from 0 to 1, and then I have 2x cube y e to the y square plus 1, and this is to be evaluated when x is 1, when x is negative 2, and we need to take the difference. Let's do that. In other words, let's use fundamental theorem of calculus. So I get integral from 0 to 1, replacing x by 1 gives me 2 times 1 cube y e to the y square plus 1. Replacing x by negative 2 gives me 2 times negative 2 cube y e to the y square plus 1 dy. Alright, let's simplify these numbers, and then we'll get a pure function of y. 2y e to the y square plus 1, and then this is positive 16y e to the y square plus 1. Well, these are two like terms. We need to add them before we integrate. So addition of these two like terms, 2y e to the y square plus 1 plus 16y e to the y square plus 1 is 18y e to the y square plus 1. Now again, variable x is gone. As I mentioned earlier, that integrating this with respect to x and replacing x by those bound will make x disappearing from our function, and you will get a pure function of y. Now you need to integrate that pure function of y with respect to y. Select the correct integration technique. We already checked earlier that we need to use u substitution. Let's use it. Start with u being inner layer of your composite function, which is y square plus 1. Replacement of dy in terms of du needs to be calculated. Seems like we need to replace dy by 1 over 2 du. Remember, u substitution is a technique to convert certain product involving composite function into the form that match with the basic integration formula. So what we would like to do here is we would like to rewrite this problem into variable u so that we can integrate it. So it's a logical process of converting everything into u, including the bounds. So let's change the bounds as well. When y value is 0, corresponding u value will be 0 square plus 1, which is 1. When y value is 1, corresponding u value is going to be 1 square plus 1, and that is going to be 2. Alright, so let's make all these changes simultaneously. Replace inner layer by u, replace dy by 1 by 2 by du, and replace lower bound by 1, upper bound by 2. Okay, this is what we are going to get if we do that. The problem becomes integral from u equal to 1 to u equal to 2. We have 18y e to the u times 1 over 2y du. Cross out the repeating part. We get u running from 1 to 2, 9 e to the u du. Alright, so this version is matching with the basic integration formula. We can integrate it without any difficulty. Right, antiderivative of e to the u is just e to the u. Remember, the bounds are already in terms of variable u. There is no need to go back to variable y. This is a very common error that students make in the quizzes and exam. Be sure that this is something that you don't do in the quizzes and exams. Plug u equal to 2, u equal to 1, and that is going to be our final answer. As I mentioned that it is perfectly fine to leave your answer in the exact form. In other words, you can leave your answer in terms of power of e or natural log of a